In this lecture segment, I am going to get you started on a problem, problem number 1.6 in Mitzenmacher and Opfer. And this problem models a phenomenon that we often see in real life called the rich get richer. And here is how this problem works. We have a bin, and we at the start of time have two balls in this bin. One is a black ball and one is a white ball. And each time step we pick one of these two balls, one of the balls in this bin uniformly at random, and then if it happens to be a black ball, we will replace the black ball and add a black ball. So, if we had picked the black ball, and then we would have replaced this black ball and added a black ball. Now, let us say the next time step we pick a ball uniformly at random and we pick the white ball. Then we will replace this white ball and add another white ball. So, this is the way this random process proceeds, and as you can imagine, over time due to the randomness in this process, one color might exceed the other color. And once that happens, now if let us say over the course of time there are several more white balls than there are black balls, then you can see how the rich get richer phenomenon comes into play here, because now you are more likely to pick a white ball, and then once you picked a white ball, you are going to replace that white ball and add a new white ball. So, the number of white balls is going to increase. So, this is in that sense it matches this phenomenon that I just talked about. So, this question, problem number 1.6, asks us to prove something about this process. This random process now proceeds until we have a total of n balls in bin. Okay. And we need to prove something about this process at the end when we have n balls in the bin. And in particular, we want to be able to prove the following statement. And this statement must hold for all k belonging to the range 1 through n minus 1. Let us make this. In particular, we want to be able to prove that the it is equally likely that the number of white balls be 1, then the number of white balls be 2. All of these events are equally likely events, and this is what we need to prove according to this problem. So, let us see how this will work, but I am only going to get you started on this problem. What I am going to prove is the case where k equals 1, and then using the idea that I use to prove this k equal to 1, you will have to, your job is to extend this to the case where k can be larger than 1. Okay. And for this we can use proof by induction. So, our base case is the following, that is at the end when n equal to 2, So, here of course, probability that the number of white balls equal to 1, and remember our k, we are going to assume the case where k equal to 1. So, the number of probability that the number of white balls equal to 1 is equal to 1, because we start out with exactly one white ball, and this matches our 1 over 2 minus 1 equal to 1, and so the base case holds. Okay. Now, what we are going to do, our inductive hypothesis is the following. We are going to assume, let us say that there are n minus 1 balls, and when there are n minus 1 balls, our assumption is going to be that the probability that the number of white balls equal to 1, that is equal to one over n minus 2. This n minus 2 is coming from the fact that we want to prove this probability to be able to form 1 over n minus 1, and here it is n minus 1 ball. So, we have to let's take n minus 2 here. Okay. So, this is our inductive hypothesis, and now we are ready for our inductive step. And for this, of course, we have to work with n balls. And let us look at the probability that the number of white balls is equal to 1. Now, think about it. How can you have one white ball after the total number of balls in the bin has reached n? Well, two things must happen. Think about the very last step. Prior to the last step, you should have you will have to have at least one white ball, because you cannot start with 0 white balls, and then you should remain at that one white ball. And in other words, in the last, when you had only n minus 1 balls, there must have been exactly one white ball, and in the last step, when we reached n balls in the bin, you should not have added a white ball, you should have added a black ball. When these two conditions hold, we will be ending up with exactly one white ball, and probabilistically speaking, here is how we can write that. So, this probability equals the probability that the number of white balls equal to 1 when bin has n minus 1 balls times the probability that the nth ball, which is black, given only one white ball amongst n minus 1 previous balls. Okay. So, this is the event that you have exactly one white ball after you have reached n minus 1 balls in the bin, and then the last ball that gets added, given that you only have one white ball amongst the n minus 1 previous balls, we are interested in the event that the nth ball remains black. Okay. So, let us work this out. What is this probability? Well, here we can take advantage of the inductive hypothesis. So, this probability is 1 over n minus 2, okay, times this probability. Here what is the probability with which the last ball will be a black ball, given that there are a total of n minus 1 balls, out of which n minus 2 are black. So, here the moment you pick a black ball, you are going to replace that black ball and add a black ball. So, that is what is going to happen. So, this probability is really the probability that you pick a black ball. So, that is times, and there are n minus 2 black balls, remember, because this is at most this is exactly one white ball among a total of n minus 1 balls, okay, because these two cancel out and you come out at 1 over n minus 1, which is precisely what we need to prove. Okay. But of course, we have only solved the case where k equals 1. Okay. What we really need to be solving is general values of k. Okay. How do we solve that? Well, the same idea can be extended. I am going to leave this part as an assignment for you to solve. The same technique can be applied, except now we need to be a bit careful. Okay. In order to achieve a final goal of just one white ball, we needed exactly one white ball in the previous step as well. Okay. But let us say k equal to, let us say 5. Okay. We are talking about the case where we are interested in the probability of achieving 5 white balls at the end of this process. Okay. But keep in mind, you can achieve 5 white balls in 2 ways. One is you could have achieved the 5 white balls at step n minus 1 when the total number of balls was n minus 1, and then added a black ball, which retained the 5 white balls. Alternatively, you could have reached the case where there are 4 white balls after the bin has n minus 1 balls, and then when the nth ball is added, a white ball is picked, and therefore the new ball also becomes white, and therefore the 4 white balls become 5 white balls. So, there is 2 ways in which you can achieve the number 5. So, that is something to think about and keep in mind while you work on the general values of k, which will be your assignment.